Okay, I think we're recording. Yep. All right.
Hey, Chris.
Mr. Dow, I would seriously put paper on the other side.
It'll be fine. Trust me. Okay.
Watch it
Here,
fall.
we'll put a bug on the other side.
See?
Okay.
That's
That way, it'll be. It won't. The bug is strong enough to keep it upright. Okay. Is it still focused on the board just fine?
Yes.
Okay. Good. I don't know why it's doing this. This thing is giving me nothing but headaches, like, the entire time. Every time I try to use this thing, like yesterday it wouldn't record correctly, and then today it's doing the weird thing where it's making the video backwards.
Well, I mean, it makes sense.
So
virtual image.
it actually shouldn't be doing that. So I don't know what setting I've changed on it. But anyway, okay. So what we're going to do right now, basically, everybody, is before we start talking about anything new, okay, we're just going to go over some examples from the homework from last night, okay? So the homework examples, basically the homework last night, the first part was checking to see if two matrices were inverses, and also to finding the inverses of matrices, okay? So, my first homework example here, we've got, excuse me, two matrices. Matrix A, which is 2, 1, 5, 3, and matrix B, which is 5, 3, sorry, 3, -1, -5, 2. To check to see if two matrices are inverses of each other, okay? All you have to do is multiply. Hey, you to the back.
Hey.
Okay.
I was just.
Could be picked up on the recording.
Needs his test.
Oh, you need your test? And I give you your test?
Yeah, I kind of did.
Okay. There.
Does Brendan take tests?
Yeah.
Yeah. Hey, what's up?
There it is. All right. Basically, so working this out here. Yes, it's fine. Sit down. Sit down, Jim.
100. Okay.
All right. Basically, what we have to do is multiply this through. We multiply it, and we see if our answer ends up becoming the identity matrix. Okay. So working this through here, we did 2, 1, 5, 3 times 3 minus 1, -5, 2, and working it out. 2 times 3 is 6. 1 times -5 is -5. Then 2 times -1 is -2 basically. And then 1 times 2 is 2. Okay. Then we repeat that for the next to find the next row. 5 times 3 is 15. 3 times -5 is -15. And finally 5 times -1 is -5. And 3 times 2 is 6. Okay. Okay, just have a seat, guys.
So
Okay.
that was the last period.
All right.
6 plus what's in
That's -5.
For Brendan.
Okay. Basically,
Wrist.
working everything out here, okay, we would actually get the numbers 1, 0, 0, 1, meaning these two things are inverses of each other, okay? Which is exactly what we're after, okay? Now, by the way, if I had flipped these around, if I do B first and do B multiplied by A, I'll still get the inverse matrix. Or sorry, the identity matrix 1, 0, 0, 1. Okay, it's kind of the nice thing about it. Yes, Jim?
Will the inverses always end in like 0 and 1? Or is that
Oh, you mean they always give me the identity matrix? Yes. Okay. In fact, that's the definition of inverse matrices, if you remember from yesterday. Two matrices are inverses. Okay. If A times B is equal to B times A, which is equal to the identity matrix. Okay. I is the typical letter you use for the identity matrix. Okay. So, and again, it's the identity matrix for that order. So if these were both 3 by 3 matrices, and we did the multiplication, we get things like this. Okay. Now, one thing to note though as well is that the identity matrices, the ones we did in class yesterday, all like the inverse matrix had a bunch of fractions involved with it, right? Well, this one doesn't, does it? Okay. And that's something to keep in mind. You're never going to be 100% sure what these things are going to look like. Also, too, it is possible, okay, to have more than one inverse matrix for a matrix. Okay, it can happen where I've got two matrices be inverses, and one matrix being the same and then a completely different matrix also being inverses. Okay, and the method we use to find inverse matrices, that finds us a inverse matrix, okay? So do keep that in mind, okay? Any questions on this right here?
No tango.
Okay, by the way, there aren't fractions over here for B because the determinant of A is actually 1, if I worked it out, okay? All right, good. Let's take a look at our next one. Okay, so our, whoops, did I go one too far? No, I just haven't. Okay, yeah, so that's basically how that works out, okay? All right, the next homework type question we had was finding an inverse matrix, okay? That is, given a matrix, we want to find an inverse for it, okay? And so this is exactly what we did here. We have matrix A is equal to 2, 0, 0, 3, okay? And what we do is we calculate its determinant first, which is what we did right here. 2 times 3 is 6, 0 times 0 is 0, so 6 minus 0 is 0, okay? And then, to figure out the inverse, we use the formula for it. The inverse of A is equal to 1 over 6, basically 1 over the determinant, times the modified matrix A. Now remember, when you modify matrix A, you flip the first diagonal and you negate the other one. Okay? But what's negative 0 equal to? 0. Okay? And in the math we do, negative 0 is just 0. Okay? There are times when you can have a negative 0. If any of you ever take statistics, negative 0 exists there. Okay? But for the math we do, there's no such thing as negative 0. Okay? Alright. Working this out then, we got that the inverse then should be 1/2. Oops, I messed that up there. It's not 1/2, it should be 1/3. Should be, no wait, I was right, 1/2. 3 over 6 is 1/2. Doy. And then 2 over 6, which is 1/3. Okay? So 1/2, 0, 0, 1/3 is our inverse. Now, what do I do if I want to check this? Make sure this is the inverse. What am I going to do?
Multiply.
Multiply. And in fact, let's go ahead and do that. Okay? So we're going to do 1/2, 0, 0, 1/3, and we're going to multiply it by the original matrix, which was 2, 0, 0, 3. Okay? Working it out, what's 1/2 times 2? 1. Plus 0 times 0, which is 0. Okay? Then with 0 times 2? 0. And what's 1/3 times 0? 0. Okay? So next number becomes a 0 there. Move on to my next row, repeat. What's 0 times 2? 0. What's 1/3 times 0? 0. And then finally, what's 0 times 0? 0. And what's 1/3 times 3? 1. So it works. Okay? Those are indeed inverses of each other. Any questions how these work here?
No tango.
How do you know, like, when you're supposed to find the
When you're supposed to? It's part of the process for doing for finding an inverse matrix. Okay. So at least for the 2x2 matrices, Jim, you have to find the determinant of the original matrix in order to find the inverse. Okay. So if I'm checking inverses, that means I'm given two matrices and I just want to multiply them to see if I get the identity matrix. If I'm given a matrix and I'm asked to find its inverse, then I know I'm going to have to take a determinant and use the formula for finding inverses. Okay? Alright, good. Alright, now the next thing we did for homework last night was using Cramer's rule to solve a system of equations. Okay? I want to basically just kind of go through that and make sure we'll get how that works here. Okay? So the homework problems were 2x2 ones. Okay? I didn't give you, I think I gave you one 3x3 system of equations, but most of them were 2x2s. Okay? So this one's number 15 here, and this is how you would work it out.
It's called Cramer's rule.
Cramer's rule. Okay? Cramer. C-R-A-M-E-R. Apostrophe S. It's his rule. Whoever Cramer was. And that's his last name, too. I don't know what his first name was.
Christoph.
Probably was Gustav.
Christoph.
Christoph. Could be Christoph. These, typically, a lot of these mathematicians are German or French, so you could pick a German name or a French name, it's probably close enough. Okay. Kind of like someone, I remember seeing kind of a joke video called Pachelbel's Rant. It's actually rather funny. It's this guy, okay, let me preface this. Has everyone in here seen Four Chord Song, or heard Four Chord Song by Axis of Evil?
You should play it.
Okay, now I cannot play it due to language. But basically what Four Chord Song is this Australian group called Axis of Evil. And they basically, start off by playing the chords to Don't Stop Believing by Journey, okay? And it turns out a ton of other songs, like a ridiculous number of songs, use those same exact chords, okay? And it ends up being 4 chords, okay? Well, the 4 chords are actually the 4 chords from Pachelbel's canon, in D. The one that goes da, 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 yeah, anyway. And so there's this guy who does what's called, there's a comedian, and you can see Pachelbel's Rant. He's got his guitar, and he's playing those 4 chords over and over and over again, and pointing out how all his favorite music ends up just being Pachelbel's canon. The thing is, he hates Pachelbel's canon in D. And anyway, but I digress. And he makes a joke that he doesn't know Pachelbel's first name, but he suspects it's probably Johann. They're all named Johann. Johann Sebastian Bach, etc. Anyway. That's a -1, yes. So this is, so what we first do is we create a coefficient matrix, okay? Matrix A is my coefficient matrix, and basically all it is the coefficients from my thing. So I have an x column, which is a -7 and the 3, then a y column, which is the 11 and the -9, and then an answers column, which is a -1 and 9. I know that looks like a -11. We'll make that look like more like a -1. How about that? Better? Okay? Now, what Cramer's rule says first is I'm going to take the determinant of my original coefficient matrix. Okay? I go ahead and do that, I get 30 as my answer. Okay? Now I'm going to hold on to that, because now to calculate x and y, I'm going to do the same thing, take determinants, but replace the column of the variable I'm trying to find with those answers. So here, the -7 and -3, that answer column, the x column gets replaced with -1 and 9, the answer column from it. Okay? Over here for y, same deal, but I replace the y column, which is the 11, -9 column, with -1, 9. Okay? So now all I do is I take the determinants of this and then divide it by the determinant of the original coefficient matrix. So this determinant divided by 30, that's going to be 9 minus 99 over 30, or -90 over 30, so -3. So x would be -3. Okay? And then I do the same thing for y over here. The determinant ends up being -63 minus 3 over 30, so -60 over 30, which is -2. Okay? And that's how Cramer's rule works. Okay? So for a 2x2 one, it's fairly straightforward, it's fairly simple. Okay? Now, you might say, well, Mr. Dowell, does matrices make these any better? This one was 2x2. And yes, I can solve this one fairly easily using substitution or elimination. Okay? But still, the exercise was to use Cramer's rule. And actually, Cramer's rule was pretty simple to use here. Okay? It works really quickly. All right? Any questions on how Cramer's rule works here? Okay, because we're going to look at a few more here. All right. I'm going to wait. I see some pins continuing to copy.
So when you're trying to find x, you don't put.
How do you determine which one to put in for trying to find x?
X? Okay, I can think of it when I make my coefficient matrix. Every column here is going to correspond to one of the variables.
Right.
So my first column here was the coefficients of x. My second column here is the coefficient of y. Okay? Well, when it comes down to solve for x, I'm going to replace the x column with the augment. Basically, I refer to it as the answers. It's probably got a better name, but I don't know what it is. So the x column, the -7, 3, gets replaced with -1, 9. Okay? But the y column stays the same because I'm not solving for y. Okay, so I'm not going to make a change there for y. Alright? And doing this way allows me to solve for x. That's how I got x equal to -3. Likewise, for y, I do the same exact thing, but this time, the x column stays the same because I'm solving for y, not x. And it's the y column that turns into the answers. Okay?
So,
And then work it through to get -2 is my answer.
so when you're finding the determinant, you just put in -7, 11, 3, and -9.
Yeah, for the original determinant of a.
Like when you're plugging in the calculator.
Yep. Okay. So for my for up here, my first one, this is what I use for my determinant. Okay. And then to solve for my variables, I take the determinant of new matrices and divide them by the determinant of that original coefficient matrix. Okay? Alright. Better? Okay. Kind of look at some special cases here. Okay? Now, here's the first one. Alright? I've got 3x plus 2y equals -2, and 6x plus 4y equals 4. I set that up into a coefficient matrix, 3, 2, 6, 4, and then augmented the -2 and the 4 on the outside. But when I calculated the determinant of this guy, I got an answer of 0. Okay? Now, that's problematic. Why? What am I going to be using that determinant to do?
Multiply by 2.
Not multiply, but
Divide by.
divide. I'm going to be divided by the determinant, right? And can I divide by 0?
No.
Not in this realm of math. I can't. So because I can't divide by 0, if I got 0 as a determinant, that means there's a big problem. And it turns out when you get 0 as a determinant for these matrices, it means that for at least 2x2 system, it means that they're parallel or they represent the same line. Okay? Basically, if the determinant is 0, the system is either parallel or collinear. Okay? Everyone got that? Alright. In this case, what do you think they are? Are they collinear or are they parallel? They're going to be parallel. The way I can tell, if they're collinear, the two lines should differ by a common factor. Okay? That is, if I multiplied one line by by whatever the factor is, I'll get the second line completely. If they're parallel, that'll work for the x's and the y's, but not the answers. And that's exactly what happens here. The bottom one is double the top one, except for my answers, which are -2 and 4. Okay? That means these have to be parallel. Okay? Never touch each other. Alright? Alright. Any questions here? How that works? Alright, good. Now,
So whenever you divide by 0, that's going to be parallel.
basically, yeah. If I have a system set up like this, when I take the determinant of the system, if I get 0 as an answer for that determinant, I know then that I'm either dealing with a parallel system or a collinear system. Okay? If these were 3 equations with 3 unknowns or more, I could be dealing with it could be parallel planes or spaces. It could be coplanar, cospatial planes or spaces. It could also be a weird situation that will happen with planes and with spaces where 2 of them intersect but don't intersect the third one. And that could also happen. But you'll still get a 0 basically out of it. Okay? Essentially you'll get a 0 and won't be able to calculate answers. Okay? Because that means there won't be an intersection. Yeah?
What if you get a 0 when you plug in to solve for the determinant of one of the variables?
Oh, okay, so for the variables if I get a 0, that's perfectly fine.
Okay.
Okay? That just means the coordinate
It's
would be
just
0.
Okay.
Okay? It's when it's because I'm going to have to divide by this determinant here that it's problematic. Okay? The flip of it, absolutely fine. Okay? Because these things could be 0. Alright, good. Any questions? Alright, and now this last one, this is just the last example I did earlier in class. I just wanted to show you a little trick for it, how to do it fine, work it out. I personally, while getting decimal answers while getting decimals as answers are fine, I don't like doing arithmetic with them. So, when possible, I'll try to get rid of them, and in this case, they were fairly easy to get rid of. Because these are all in terms of tenths, I can just multiply everything by 10 and convert it into regular old numbers and do the work with that instead. Okay? And so that's exactly what I did. Basically just shuffled the decimal place over 1 and changed this to minus 4x, 8y, 16, then 2x, 3y, 22, and worked it out from there. Okay? Any questions? Alright. And by the way, the answers of these actually do not come out to be very pretty. For the x's, I got 4.571, and for the y's, I got 4.286. Okay, and looking up in the back of the book, that's because these are in terms of sevenths. Actually, you convert these to a fraction. It'd be like I think the first one would be like 30 something over 7, and the second one would be also, I think the second one is 30 over 7, and the first one, this one right here, is like 33 over 7 or something like that. Okay, that's what they come out to be. All right, any questions? All right, excellent. Well then, what we're going to do now is we're going to move on to new stuff. So we're going to be done talking about matrices for a bit, okay? Basically, they will come back a little bit later, because what we're going to do is eventually we're going to talk about how to solve a nonlinear multivariable equation, okay? But until then, we're going to be talking about something slightly different, okay? And that is actually what a nonlinear multivariable equation might look like, okay? So what we're going to talk about now is what's called analytic geometry, okay? Basically what analytic geometry is in a nutshell, it's applying algebraic rules to geometric systems, okay? It's expressing these things from geometry, some common things from geometry, in terms of x and y on our xy plane, okay? We're going to break it up, the kind of the things we're going to talk about in analytic geometry. We're talking about 5 different things. Circles, which you should know what a circle is by now. If you don't, no, I'm sure we can find a kindergarten class. I think Grimes has one you could go to. Ellipses. An ellipse is a fancy word for a circle. Sorry, not a circle, an oval. Okay. The term in math for an oval is an ellipse. Okay, so if you see ellipse, just think oval. Okay. Parabolas, we've seen those before. Okay, those have the U shapes. A new one called a hyperbola, which actually is just a parabola turned on its side, so you get it to be like this instead of like this. So instead of being a U, it's a kind of cutaway like that. Okay. And a last group of things called parametric equations, which is where basically with parametric equations you have a separate x and y basically equations. And the one equation tells you what's happening with x, the other equation tells you what's happening with y, and you can make some pretty crazy looking pictures out of it. Things that spiral, things that like make clover shapes, etc. Crazy swirls, heart shapes, that sort of thing. Okay? Now, like a swirl, like you could with a parametric equation.
Oh, a swirl.
A swirl, yeah.
I thought you said
A whirlpool. A squirrel?
Yeah, okay.
I'm sure with the right set of parametric equations you can make something that looks like a squirrel. But no, I'm talking about swirls instead. Yes, Luke?
Because parametric equations are part of the conics.
No, they're not technically conic sections.
Oh,
Okay.
shoot.
That's why they're separated. Okay? The first 4, though, they're a special class of equations called conic sections. And the reason why they're called conic sections is they can all be represented by cone, or actually more properly this hourglass looking shape. Okay? Every single thing here can be thought of as a cross section, okay, of these cones basically. Alright? Kind of stacked up one on top of the other. I wish I had a cone in here I could use as an example. Okay? But to start with, if I cut a cone straight across, what shape am I going to get? I'm going to get a circle, right? Cutting it straight across gives me a circle. If I cut it straight across, but don't do it exactly straight, kind of do it at an angle, what do you think I'm going to get?
Oh, what's this?
An ellipse. Okay? Basically, kind of cut at an angle. All right? Likewise, if I cut it if I don't cut it directly across, but cut it kind of more at a very extreme angle, like down here, I'm going to get a parabola, okay? And if I cut it straight up and down, as opposed to left and right, I get two shapes, and they're called hyperbolas, okay? And they're up and down like that, okay? By the way, points and lines can also be found, can also be thought of as a conic section. A point on a graph, okay, is where the two cones meet, okay? And a line is the edge of the cone going through that point, okay? So everything we've dealt with this regular old x and y, either be they a point or be they a line on the graph, we can actually still model using a conic section, okay? So basically everything we're going to do now is going to be keeping this in mind when we deal with the conic sections, okay? Any questions about that?
Where's the parabola?
Oh, the parabola would be like cutting it at an angle, not through. So it'd be like if I had a, let me draw it on the blackboard over here, a little bit clearer. So it'd be like if I had, this is my cone, right here. To get the parabola, I cut it like this, okay? And what I'm going to get is basically, if you were to map out that shape with that cut, it would be parabolic in shape. Its cross-section would basically look like that, okay? That's how the parabola works, okay? Any questions there? All right, good. Okay, now that brings us in mind to our next thing, which is a circle, okay? And we're going to describe circles now in terms of x and y, okay? So we're going to try to think of what a circle actually is, okay? So I'm going to ask you a question, all right? What is a circle? Okay? Tell me what a circle is. How do I make a circle? Yeah?
It's a bunch of lines coming out from one point that all go the same length.
Okay, good. Basically, kind of what you said, a variation on that, is basically it's a bunch of lines going through a common point in the center that are all the same length. Okay? You can think of a circle that way. A slightly better definition based off of that is that a circle is a collection of points that are equidistant from a common point, okay, between them. All right? And in fact, that is the proper definition for a circle. A circle is a curve, a collection of x, y points that are equidistant from some common point in between them all. Okay? And that's going to be the key with circles. The points are equidistant. That is, any point on the circle is the same distance away from the origin as any other point. Okay? And the center of the circle is going to be called the origin. Okay? So somebody earlier said circles have a center and an edge that is a radius length away. Okay? Which is basically sort of what you were going at. Okay? So, when we talk about circles, we want an equation that will model this right here. Okay? And luckily we have one. And as soon as I see people stop jotting down notes, I will go ahead and move pages and look at it. Okay? Gesundheit.
That's German, right?
Yeah. Or basically, bless you.
Du bist scheiße.
Okay. That is also German for something I cannot repeat in class. You shouldn't say. I know what it means.
What does it mean?
I'm not going to tell you in class.
Yeah, right. You don't know what it means.
How fast can someone get on?
I don't know. I've gotten it pretty fast. The problem is eventually it just flies off because the torque on it's greater than the magnet on it. All right. Moving quite along. Okay. So here's an example. That there is a circle. Okay. The thing is, the center of the circle is right here. Every point on the edge of the circle is the same distance away from the center. Okay? They're all the same distance away. That distance is called the radius. And this circle here, I made it to be 2. Okay? Now, basically from that, though, I can create an equation that will help me govern how my circle works. The equation for a circle is going to be x minus h squared plus y minus k squared equals r squared. r squared is the length of the radius squared, okay? And x minus h and y minus h, those are the x and y components of the circle, okay? The h and the k there, though, are adjustments for the origin. Basically, they tell me where the center or origin of the circle is. Okay.
This looks like the vertex equation.
It looks very much like the vertex equation for a parabola, okay? The difference though now is we've added a y in here instead, okay? And that's actually on purpose, okay? The vertex form of a parabola is related to this, and in fact, that vertex form of the parabola is essentially a modification of the conic way of writing a parabola, okay? The difference is that we've just, instead of making it x and y equal a number, we've made it so that x equals y in that case, okay? But very, very good eyes, very good part. So yeah, basically, the h and the k just tell me where my origin is. So here, for this circle, my origin is 2 in the x direction and 4 in the y direction. So the equation, and the radius is 2, so the equation for the circle would be x minus 2 squared plus y minus 4 squared equals 4, okay? And again, r is my radius, so if I took 4 to the square root of it, get the radius of 2. And h and k are the x and y coordinates of my origin. So h would be positive 2, and k would be positive 4. So again, when finding the origin, just like you would with a parabola, you flip the sign, okay? The signs here are opposite of what they are going to, okay? Think of it this way. It's what I would need to do it would be what I need to add or subtract to x or y to adjust it back down to the origin, okay? Everyone got that? All right, good. Okay, so this is the equation of a circle, all right? And this is basically how they work. Tomorrow what we're going to do is we're going to do basically work with sketching some circles and also working out a little bit more with the equations of them. Because these equations for circles can get a little bit nastier than this, okay? It's something to keep in mind, all right? Any questions on anything we've gone over today? Okay, your homework should be up on Canvas, and y'all have a good afternoon.
Bye, Brendan.
Okay. Bye-bye.
Now,
Yep.
let's go.